Hey everybody, you can see by looking at the page here that we're going to do a little bit of work out of the CPM book today. What we're going to do is cover section 623 and 624, and I think they fit together quite well. And the idea here is just to, again, introduce you to some ideas in statistics. And what we're going to do is talk about cause and effect in 623, and then we're going to talk about the correlation coefficient squared in 624 and how that's important. By the end of this, I hope you're more comfortable with both of those terms. Okay, so let's take a look at this one first. Association is not causation. So what we're talking about is if we see a strong association or any sort of association, does that mean we necessarily know the cause? So if we look at this first part, it says a study found that the more hours students spent on activities outside school, the higher their grades tended to be. Does that mean if you go sign up for more activities, your grades will go up? Another study found a link between how often you brush your teeth and a reduction in heart disease. Does that mean if you brush your teeth twice a day, your heart will be healthier? Right. So in terms of those two questions, I think you can pretty clearly say, well, no, right? If you sign up for more activities, that does not necessarily mean your grades will go up. And if you brush your teeth twice a day, that does not necessarily mean a reduction in heart disease. There are so many other variables that have to be taken into account. So what we're trying to do here and what this text is trying to do is caution you about making assumptions based on associations, right? So as a consumer of statistical information, you need to be aware of the distance between association and causation. Today's investigation will explore that difference. Right, so the idea is be careful when you're reading any statistics, and especially if people are trying to get you to believe their statistics without going into much detail about the studies. All right, let's take a look at this one. We're going to take a look at question 680. I think this one actually points out pretty clearly what we're talking about. So it says here that the mayor of Smallville finds the following graph in the town's annual financial report. So if you look over here at the graph, you can see this report shows an association between the number of firefighters at a fire and the amount of damage done. Right? So then Part B here says the mayor immediately orders the fire department to send fewer firefighters to each fire so that there is less damage. Why do you think the mayor said this? Do you agree with the mayor's decision? Explain why or why not. All right, so pause the video for just a bit, answer that question on your own, and then I'll explain the book's thinking and my thinking. Okay, so clearly I can understand why the mayor might say this based on the graph. Of course, the mayor seems a little short-sighted to me, but anyway, it does appear from the graph that the fewer the firefighters, the less damage. Right? So if you weren't really thinking, you might think, well, I guess more firefighters must cause more damage. Obviously, that makes no sense at all. So there are other factors that need to be taken into account here, such as why would more firefighters go to a fire? I bet this is what you said, right? More firefighters would go to a fire because it's a larger fire. And if it's a larger fire, there's probably more damage. And who knows, there might be some other factors as well. But this is the mayor making a mistake that association is causation, that the number of firefighters are what is causing the damage, right? Not thinking, not thinking. 681, similar. A dietitian studying the benefits of eating spinach surveyed a large sample of individuals. She recorded the amount of spinach they ate and their physical strength. The dietitian found the spinach eaters to be much stronger than non-spinach eaters. The next day, the newspaper headline was, Popeye was right, eating spinach makes you stronger. Do you agree with the newspaper? Do you agree that if you eat more spinach, you will go stronger in muscles and increase your strength? Right? So answer that question, right? And for letter B, it says the dietitian correctly found an association. What could explain this association other than spinach makes you stronger? right? So again, jot your own ideas down, but my ideas include something about health conscious people tend to eat more vegetables, and that would include spinach. In fact, I have some friends who are very health conscious. They drink green smoothies. Those things have a lot of spinach in them and kale and that type of thing. And guess what? They also work out. So a lot of people who are really health conscious, not only do they eat better, but they also exercise more, lift weights, and that type of thing. So those might be some other factors there. All right, so that brings us to the important term in this lesson, and that is lurking variable. So a lurking variable is a hidden variable that was not part of the study. The size of the fire in problem 680 and the amount people work out in problem 681 are lurking variables. A medical study found a strong link between the number of hours high school students wear a helmet and the number of concussions, head injuries. However, it's unlikely that wearing helmets causes head injuries. Can you think of a lurking variable that might explain this association? And again, you'll see on the Google Doc, I want you to jot some ideas down there about the lurking variables, but I'm thinking about things like contact sports. That's why people would wear a helmet, because they're playing contact sports, and then they're apt to get injured more. Maybe biking, motorcycle helmets. They didn't really say what types of helmets, and there are high school students who do drive motorcycles, so maybe it's that. There are a lot of lurking variables that could be possible here. Okay, so you guys, that's it on 623. Just the idea of paying attention to association not being causation, and getting the definition down of a lurking variable. All right, we're going to move along now to section 2.4. Section 2.4 is really about making sense of the correlation coefficient in regular daily situations, and we're going to focus on the meaning of R squared. And I think I said in the last video, that's really the last piece that we're going to be doing. All right, so what I'd like to do is just start right away with a problem here, and I think R squared can be explained pretty well by looking at this problem in 691. All right, so it says here that Karen discovered that a human's height is associated with their forearm length. Karen is curious whether height is also associated with foot size. It wasn't practical for Karen to measure her classmates' feet, so Karen collected the following shoe size data from her classmates. It says here to read the math notes box. We're not going to do that yet. I want to wait and do that after we've looked at some examples. So let's take a look at this, and then we'll go to Desmos calculator and see what they do. But you see, Karen has collected data about shoe size and a person's height in centimeters, and she has placed it on a graph here. All right, I'm going to expand the graph to the Desmos graphing calculator. All right, and what I want you to notice is right down here. So she's got all of the graph in, all of the data in here. CPM did this for us, by the way, which is really nice. What I want you to look at here is this information that comes up after putting in the equation for the regression line. The pieces we're going to focus on are right here. So the correlation coefficient is 0.8617. When you square that, you get 0.7424, and indeed 0.8617 squared is 0.7424. Right, so I'm not going to go into all of the reasons that this works. I just want to explain to you what this means then. Okay, so listen carefully to this and see if this makes sense to you. What we can say now that we have R squared is that, and this is rounded, 74% of the variability in human height can be explained by a linear relationship with shoe size. Right, so we can think of this R squared as a percent. Oh, that's a pretty good percent, right? So 74% of variability in human height can be explained by a relationship with the shoe size. Now, there are other factors. I mean, there's a 26% that does not seem to be related to shoe size, and maybe that's factors like a person's health, Maybe it's related to nutrition. Sometimes people have disabilities that mean their shoe size doesn't match their height. So there are other variables. All right, so that's the first example of how we can interpret R squared. And that's as far as we're going to go, is just taking a look at R squared and seeing, well, how does that relate to the real world? Let's take a look at this one. Suppose Elise collected the following data for 5 random students in her class. So this is a very small sample, but she also collected data on shoe size and height. Well, if you look over here at the graph, you can see that all of those are on the same line, right? Again, not realistic, but the text put this here so that you could actually get a sense of how that works in terms of R and R squared. Okay, so you can see they've already put in the formula for the regression line. The correlation coefficient is 1, which means that R squared is 1, which means that in this case, 100% of the variability in height can be explained by a linear relationship with shoe size, meaning all of it is related to shoe size. All right, so I'm hoping you can see, okay, that makes sense because every single point is on the line, right? If we were to plot the residuals, you can see that the residuals are all right on the 0, so there's no variability. The residuals are all 0. All right, does that make sense? And again, this is not realistic at all, but it's just to make a point. All right, then this one here, okay, so Holly created this scatter plot shown at right for the girls in her class. I hope you can see by looking at this that there's no correlation at all, right? So this was the score on the Chapter 5 test compared to the height of the girls in the class, right? So the correlation coefficient in this one is 0. If we tried to actually put in a line of best fit, what would happen is it would put some sort of horizontal line in here right in the middle of all of this data. And you can see if you look, it would be about the same number of points above and below. So Holly can't really make any predictions about average height based on test scores. The only thing she could calculate was that the average height of the girls in her class would be 162 centimeters. So again, there would be a horizontal line at 162. And remember, a horizontal line has 0 correlation. So you would say 0% of the test scores, or 0% of the variability in height can be attributed to test scores. Right, so again, they put these 2 extreme examples so you could see how that goes. All right, we're going to just scroll down now to the math notes. We're not going to do any more of this, and I'm hoping this makes more sense to you now that we've done a couple of problems here. So I'm going to read aloud. You can just read along with me. The correlation coefficient R is a measure of how much or how little data is scattered around the least squares regression line. It is a measure of the strength of a linear association. Correlation coefficient can take on values between -1 and 1. If R equals 1 or R equals -1, the association is perfectly linear, okay, like Alyssa's data there. There's no scatter about the LSRL at all. A positive correlation coefficient means the trend is increasing, slope is positive, while a negative correlation means the opposite. A correlation coefficient of 0 means the slope of the LSRL is horizontal and there's no linear association whatsoever between the variables. Correlation coefficient does not have units, so it's a useful way to compare scatter from situation to situation, no matter what the units of the variables are. The correlation coefficient does not have a real-world meaning other than an arbitrary measure of strength. The value of the correlation coefficient squared, however, does have a real-world meaning. R squared, the correlation coefficient squared, is written as R squared and expressed as a percent. Its meaning is that R squared percent of the variability in the dependent variable can be explained by a linear relationship with the independent variable.